Oh, hello. Have you ever taken a thermodynamics course? Have you ever seen a professor say all of these words as if they were in any way indistinguishable? Have you ever looked up their definitions and realized, well, some of these words are exact opposites, even though they look identical? Some of these words actually mean nearly the same thing as something else, and some of these words mean nothing at all. I know who's responsible, and you may be entitled to compensation. Today we're going to talk about three things. I want to say the most important, but I'm going to hold myself back and say the most useful physics equation. We're going to talk about the virial theorem, and we're going to talk about the Gravo-Thermal catastrophe. We're going to start with Rudolf Clausius, who was born in Prussia, which doesn't exist anymore, in 1822. He wrote his PhD thesis on why the sky is blue and why sometimes the sky is red or pink or orange. The shade on this Wikipedia article. Later, Lord Rayleigh would show that it was in fact due to the scattering of light, but regardless, Clausius used a far more mathematical approach than some have used. All my homies think that Clausius is more mathematically rigorous than Lord Rayleigh. I didn't pull that off, did I? It's fine. It's fine. In 1865, Clausius introduced the definition of entropy, which you can see why we're blaming him for this whole situation, the first and second laws of thermodynamics. Of course, these two laws of thermodynamics had been stated before in other variations, but he stated them in such a way that it made him famous, and his are often quoted as the laws of thermodynamics. Of course, 1865 was a big time for thermodynamics. You got to think steam engines are coming around. The physicists are really focusing on how can we get more orphans in the orphan crushing machine? Suddenly big business is interested in what physics is doing. So the rise of thermo is really related to the rise of industrialization. Let me read you the way he stated his two laws. First, the energy of the universe is constant. Perfect. Conservation of energy. We got it. 2. The entropy of the universe tends toward maximum. So entropy is related to the lost energy when you are using energy to do work. The second law of thermodynamics is, if you're interested in crackpot lore like me from afar, please stop emailing me. You will know that crackpots don't like the second law of thermodynamics because it means you can't have perpetual motion machines. It's always friction, guys. It's friction. Okay? Sorry. So if you are putting energy into something to do work, you can't get all that energy out. And entropy is the stuff that's lost. So eventually, should all energy go to entropy? So another way to state the second law of thermodynamics is to say that heat will always follow the gradient of temperature. It will go from a hot thing to a cold thing every time. And if you want to force cold to go to hot, you have to apply energy to that. That's why air conditioning is so expensive. Like me, Clausius is obviously a huge lover of words and their meanings and their definitions and where words come from. So he's this premier in the field of thermodynamics. He's naming everything. I'm not a big fan of the way it was done, but it's fine. Let me read you his definition of entropy. I prefer going to the ancient languages for the names of important scientific quantities so that they may mean the same thing in all living tongues. I propose, therefore, to call S. Dude, what is S? Why did you call it S? If it's entropy, why is it S? Why? To call S the entropy of a body after the Greek word transformation. I have designedly coined the word entropy to be similar to energy, for these two quantities are so analogous in their physical significance that an analogy of denomination seems to me to be helpful. And here's where I'm not liking Clausius so much, because he's saying that entropy is so related to energy that it's important that they have the exact same definition. And it's so confusing, my dude. If it's the same thing as energy, why does it have a different name? And if it's not the same thing, why would you give it a name that's oh so similar? Why? So the Greek word he's referring to is trope? Just for fun, the Greek word that makes energy is ergon, which means work. So Leon Cooper, who is a Nobel Prize winning physicist in 1972 for the BCS theory of superconductivity, Cooper is the C. He wrote a textbook on physics, and in it he said that Clausius succeeded in naming entropy a word that means the same thing to everybody. It means nothing. And yeah, dude, I'm not the only one that is confused in thermo by the word entropy. It is very confusing. I'm sorry. Thanks, Clausius. But entropy is a totally different video. All this work that Clausius did goes into the kinetic theory of gases, a very successful theory. In this theory is where we will find the most useful equation in all of physics. You could make an argument for the most important, but I am really going to stick all my poker chips and say, fight me, the most useful equation in all of physics. Are you ready? Do you want to guess? It's PV equals nRT, the ideal gas law. PV equals nRT. The ideal gas law explains the behavior of gases. P is pressure, V is volume, N is the amount of the gas you have, R is the constant, and T is the temperature of this gas. If you're gonna memorize a single physics equation to like apply to your daily life, this one's it, all right? You know, how come when you open a champagne bottle, a little cloud forms? PV equals nRT. How come actual clouds form in the sky? It's exactly the same explanation. It's PV equals nRT, babe. How come if you like blow air out of your mouth, even though the air in your mouth is at like 98 degrees, it feels cold? Well, it's PV equals nRT. How come every single winter, the first night, it's like real cold, you get in and start your car and your tire pressure light is on? Well, guys, it's PV equals nRT. The most useful equation in all of physics, all the time. Let's move on to the virial theorem. In 1870, Clausius wrote a paper on the mechanical theorem applicable to heat. And hey, I have it right here. This paper is like shockingly readable for like a modern reader. It's crazy. And in this paper right here, he, for the first time in all of physics, comes up with the virial theorem. So to start our discussion of the virial theorem, what is a virial? What is that? Well, why don't we read from Clausius? We will therefore give to the mean value which this magnitude has during the stationary motion of a system the name of virial of the system, from the Latin word v, force. In relation to these two magnitudes, the following theorem may now be advanced. The mean v viva of the system is equal to its virial. The mean v viva of a system is equal to its virial. The mean v viva of a system is equal to its virial. I hate this for us. The mean v viva. What is any of that? So v viva, I think, so v is Latin for force, and viva means like living, alive. So v viva is living force, and virial is the force that's equal to the mean v viva. So let's be done with Clausius. I can't do this anymore. Like, it's the same words. You can't just put the mean v viva is the virial of the system. What does that mean? I'm gonna switch to astronomy. Wait here. So we're gonna leave Clausius behind. I'm sure he's great. It's not you, it's me. Instead, I'm gonna follow the derivation for the virial theorem I first saw in this book, which you've probably seen me hold up before. And it's actually the derivation from Fritz Zwicky's 1937 paper where he found dark matter. So that paper is also really, really readable. I will link that down below as well. Okay, so we're gonna derive the virial theorem starting with Newton's second law. So the sum of the forces on an object are equal to the sum of the masses inside there times the acceleration. Great. The virial is like an energy-like thing. So we are gonna take this whole thing and multiply it with another. So we get Fi xi. All right, let me change colors here. This is the virial. So this is what Clausius was talking about when he was talking about the virial. It's a work-like thing. Force times distance is work. Think of it like that. Sorry to all the physicists who would have a better explanation for this outdated esoteric thing that no one uses anymore, right? Does anyone use the virial? If you are a working physicist and you use the virial, send me a note. Okay, this is the change in momentum of inertia. And this last thing here is kinetic energy, like, right? Ish. It's kinetic energy is 1/2 mv squared. This is mv squared, so it's kind of 2 ke. All right, so this actually goes to 0. We're averaging over the system over all time, so we don't expect the momentum of like the bodies to interfere with each other. So what we get is time average of the virial is equal to the negative time average of 2 times the kinetic energy. This is the virial theorem. The mean v viva of a system is equal to its virial. We did it. This is a form of the virial theorem. We kind of did it. Let's do an example. Imagine you have a box of helium. Why am I drawing a box? You know what a box looks like, and there's lots of gas inside. And we want to look at how the virial theorem applies to this problem. What is the kinetic energy of a gas? I'm not going to derive this for you. 3/2 nRT. There's a lot of trust in this math here. Let's look at what the virial of this guy is, though. So what is applying a force to the gas inside of our box? It's the pressure of the walls, right? It's an extrinsic thing that is applying this force. So what that's going to be is the pressure on the walls. So you have a little area term dotted into X. This is the virial of our gas. Let's take this further. And we can use the divergence theorem to get this.
And we can take this further.
We get minus PV with a 3. Great. So now let's look at the virial theorem again. You get the time average of this equals minus 2 the time average of kinetic energy. So you get minus 3 is equal to minus 2 times 3/2 nRT. Oh my goodness, you guys, you just recover the ideal gas law, PV equals nRT. Oh my gosh, I didn't even plan for that to happen. Wow, the most important equation in physics right there from the virial theorem. My goodness. So we paused our derivation of the virial theorem from Zwicky's paper to look at an example with gases, but Zwicky was dealing with gravitationally bound systems, like giant stars, clusters. So we're going to continue our derivation of the virial theorem, but we are going to use it specifically for gravitational potential energy. So rather than our box where the pressure was applying a force from the outside, the force on our gravitationally bound stars is gravity, which is an intrinsic property to that system. I'm going to use something called Euler's theorem. I'm not going to prove it, I'm just going to use it. If you want to look it up, this is how you spell Euler. If you're like me and you learn most of your physics from practicing problems from textbooks, it'll be helpful for you to know that this is pronounced Euler and not Euler. So when you're standing in front of all the physicists at Jefferson Lab in 2010 and you say Euler, no one will laugh because you know it's pronounced Euler. Okay, here's where we were in our little derivation, and we're going to apply this to a gravitational system, so we're going to use Euler's theorem. So Euler's theorem says that we can relate this to the potential, like this, for a homogeneous function. And that means that I can replace my virial with potential energy, because that is the force, the virial, in a gravitationally bound system. Now this is probably the form of the virial theorem that you've seen. Great. Let's talk about total energy for a second. So if E total in like a gravitationally bound system of stars, is going to be the potential energy plus the kinetic energy. But we know that the potential energy is related to 2 times the kinetic energy. You get that the total energy of the system is a negative. So let's write down the virial theorem for a gravitationally bound system. Remember, these are time averages.
Okay, we've all gone too big too fast and then run out of room. You get that poster board up and you're like, I don't need to trace it. I know how big letters should be.
Okay, let's do another example, because Zwicky was looking at galaxy clusters. So the kinetic energy of a galaxy cluster is just going to be 1/2 mv squared, and we will keep our little time average over the velocity. The potential energy, of course, this is a simplification. We're just assuming a nice spherical potential. If we look at the virial theorem, we get 1/2 mv squared is equal to minus 1/2 the potential energy. So we can rearrange this to solve for mass, which is what Zwicky was trying to do, right? So our negatives cancel, our 1/2s cancel, one of the mass is canceled, and you get m is equal to r times the time average of your velocity squared over g. The top 2 things you can measure, and the bottom thing is a constant. And this is how Zwicky, using the virial theorem, measured the velocities inside the cluster and got to the mass, and found that that mass was way higher than what he measured by any other method. This is the first evidence for dark matter. We used the virial theorem. Very cool. So now we know the virial theorem, and we can move on to the Gravo-Thermal catastrophe, which is just a very cool name. I'm going to read to you from a paper by Lynden-Bell and Roger Wood. Have I ever mentioned Lynden-Bell, my favorite physicist ever, on this channel? Oh my goodness. Okay, let me read to you from this paper. Self-gravitating systems have negative specific heats. Thus, if a heat is allowed to flow between the 2 of them, the hotter one loses heat and gets yet hotter, while the colder gains heat and gets yet colder. Evolution is thus away from equilibrium. There you go. I don't even have to talk about the Gravo-Thermal catastrophe, because Lynden-Bell can say it in 2 sentences, and you're like, phew. But we should probably get into a little bit. Let's talk about heat capacity. So heat capacity, also from the thermo days of steam engines, is how much heat you put into a system to raise its temperature. So you're adding energy to something and the temperature goes up. Imagine boiling water. You increase the little fire beneath your water, the temperature in the water goes up and it boils. You added energy, temperature goes up. That's a positive heat capacity. However, when you look at the virial theorem for gravitational systems, you see that kinetic energy is equal to negative energy. So if you add energy into a gravitationally bound system, you are going to make it less negative, which means that the velocity is going to go down. When you add energy to a gravitationally bound system, it gets colder. That's confusing. We experience mostly things with positive heat capacities, right? Like if I take a piece of ice and I rub it in my hands, adding energy to it, it melts, right? It gets warmer. That's what we expect to happen. If you add energy, things get warmer. If you have a gravitationally bound system and you throw energy into it, it gets colder. Let me do an example. I have a cartoon here, hopefully. It's a little cartoon of the solar system. To first order, the solar system is just the sun, which makes up 99.9% of the mass, and also Jupiter. Everything else is like third order effects. Nobody cares. So you have a system of gravitationally bound objects, the sun, and a planet going around it. What would happen if you threw energy at Jupiter? Well, it would move to a larger radius, right? So you've given Jupiter energy, it moves out. Planets that are further from their sun orbit more slowly. So you threw energy at Jupiter, Jupiter moved further from the sun, and the temperature of the system went down. You gave it energy, and it got colder. That's crazy. So imagine you did this with 100 million particles instead. You throw energy in, they all move to larger radii, the whole system gets dramatically colder. The velocities go down. That's how we measure temperature in a system of particles, by their velocities. You throw energy in, temp goes down. Let's think about Clausius again. and his second law of thermodynamics, right? Heat is going to flow along the gradient to colder areas, right? So if you have a nice hot cup of coffee and you set it on the counter in a room that's room temperature, the heat from the coffee is going to flow into the room, right? The coffee will cool down. The room will just get ever so imperceptibly hotter, and the thing is now in equilibrium. Now let's think of that in terms of like a cloud of gas in space. Imagine you have a little overdense region and it's hotter than the surrounding area. So it's going to emit radiation because heat flows from hot to cool, right? And because that energy went down, remember the virial theorem, if the energy goes down, the kinetic energy is going to get more positive, which means this thing that just emitted energy to lower its temperature is going to get even hotter. And now it's much hotter than the surrounding area, so it's going to emit more energy. It's going to get even hotter. That's the catastrophe, right? It's this runaway process. These things can never be in equilibrium. The more energy it gives, the hotter it gets. The more energy it gives, the more hotter it gets. They will never meet. They will never be in equilibrium until something happens. Let me read the words of Donald Lynden-Bell again. Self-gravitating systems have negative specific heats. Thus, if heat is allowed to flow between the two of them, the hotter one loses heat and gets yet hotter, while the colder gains heat and gets yet colder. Evolution is thus away from equilibrium. So if our little interstellar cloud of gas is getting hotter and shrinking and getting hotter and hotter, that's like how stars form, right? It's shrinking, it's getting hotter, it's emitting radiation to move heat from here outside, but that just makes it hotter. Oh my goodness. I've mentioned on a video before that people did not know how stars worked until relativity. That's because they thought that stars that existed in our universe were just in the process of collapse like that. They were emitting radiation as the gas collapsed. And because of that, they thought the lifetime of stars was like 10,000 years. So in the 1800s, you will have arguments between scientists where rock doctors will be like, I found this 2 billion year old rock. And space doctors will be like, well, explain how you can get a 2 billion year old rock when stars are only 10,000 years old. Explain it to me. Of course, now we know that gravitational collapse happens and happens and happens until that little guy gets dense enough to start doing fusion. And once you start doing fusion, you have a bunch of radiation going out that supports against the pressure going in. And so you get a nice, happy equilibrium star. That's the thing that changes, that makes that process go into equilibrium. Let's talk about black holes. Based on the discussion that we just had about the virial theorem and the Gravo-Thermal catastrophe, do you think that black holes are hot or cold? If I was teaching a class, I would like pause and wait for someone to answer, and everyone would hate me, but it's like such a good tool to get people to answer questions. I'm like giving you time to think about it right now. Okay, here's the answer. If you have a giant supermassive black hole at the center of the galaxy, it's got a big accretion disk. It's like sucking in material. If it's gaining energy, let's look at the virial theorem, that amount of energy is getting less negative, which means the temperature is going down. I just said less negative and pointed up. That's because the overall number, like if the energy was 100, it gains energy, it becomes less negative, and the kinetic energy gets smaller, so it is colder. So giant big black holes at the centers of galaxies have to be cold, and the more material they accrete, the colder they get. I'm sure there's a Stephen Hawking equation I can put up that agrees with what I just said. But think about tiny black holes. Like if you have an Earth-sized mass shrunk down to like this big, and it's a tiny black hole, it's not going to be big enough to have a huge accretion disk, so it's not going to be accreting a lot of matter, but it will be ejecting radiation via Hawking radiation, right? If we look at the virial theorem, it is losing energy, which means its energy is becoming more negative, which means its temperature is becoming more positive. The kinetic energy is increasing, it's becoming hotter. So big black holes are cold, small black holes are hot, and they are evaporating. And the hotter your little tiny black hole is, the faster it evaporates. It's essentially just boiling away. That's also the Gravo-Thermal catastrophe. That outside the black hole is colder than our tiny black hole, so it just starts throwing energy out. It's getting hotter and hotter and hotter, and eventually it's gone. and it never reached an equilibrium. There was never an environment where that really hot, tiny black hole could exist in equilibrium with the outside, so it just disappeared. That was the thing that ended the Gravo-Thermal catastrophe. The catastrophe is that you get this runaway change. If you have something getting colder and colder and something else getting hotter and hotter, they will never meet each other. It's a catastrophe. Fun. So we just did the virial theorem in classical mechanics. Classical mechanics is, of course, an old branch of physics that has now branched off into quantum mechanics and also general relativity. So a really fun thing to do, don't make fun of me, you're here, you've made it this far into this video, you're gonna think it's fun. A fun thing to do is to get your classical mechanics results and check it to make sure that quantum mechanics or general relativity meet that expectation at the classical limit. So what I will do for you now is derive the virial theorem in quantum mechanics. I'm going to use the relationships and notations from quantum mechanics, so your Hamiltonians, your psis, your bras, your kets. I hope even if you don't know that math, you can still follow along. Let's start with the expectation value of momentum dotted into our position vector. I'm going to call this equation 1. Again, this is bracket notation. Let's look at the commutator here. Okay, I'm going to call this one A and this one B. Let's start with A. Don't make fun of my brackets. Drawing is hard. Where V here is the potential, have I mentioned that P is the momentum vector, M is going to be the mass of our little particle. All right, now let's look at B. Oh, why did I draw an E? It's fine.
Why can't I draw a bracket?
Okay, so now we can take A and B and put them back into equation 1 right there, okay? And this will go on dy dz, and then we'll put in our B. This will go on for py, pz. Okay, so this goes to 0 with the same steady state approximation we made with the classical mechanics virial theorem. Oh wow, the sun. This is fine. No one can see this. I'm in the corner right now, right? Okay. This here is going to look like negative del potential dot r. And then this, and it's real nice how our i's and our h bars all cancel out. We get p squared over m. So this is 0. This is actually our virial, just like before, and p squared over m is 2 times the kinetic energy. So this is the virial theorem in quantum mechanics. Look, we got our little virial. We did it. Let's do an example. Let's use the Coulomb potential, where V is equal to Z E squared 4 pi E naught R. All right, I'm not going to prove any of that. That's fine. Okay. So we're going to do our virial theorem. Let's look at this with our Coulomb potential.
potential and force.
It's just going to be equal to the negative of our potential, which just for convenience, I'm going to call potential energy. That's what I'm doing, just to make it nice and match. So if we go back to our 0 equals minus del V dot R plus 2KE.
And we plug in our minus PE.
And this gives us the virial theorem we were working with the Gravo-Thermal catastrophe. So yay, quantum mechanics works. Okay, I'm gonna leave it as an exercise to the reader to do the general relativity version of the virial theorem. It's got a bunch of tensors and I don't wanna write that down. All right, well, what do you know? It's PV equals nRT. So in this house, we love and support PBS. Like, we love the documentaries. We especially love the Sesame Street and the Daniel Tiger and the Free Kids app with the games. But
of all the objects in the cosmos, planets, stars, galaxies,
I thought it would be funny to do the Gravo-Thermal catastrophe in the style of NOVA, which it's fine. It's fine. Imagine two systems separated by temperature. You see, the hot body loses energy and it gets hotter, according to the virial theorem. Imagine that. How could this happen? According to the second law of thermodynamics, heat will flow from the hot body to the cool body. What happens when these systems are bound by gravitation? Imagine you're just building a fire to boil water, and the more sticks you put on the fire, the colder the water gets, and eventually you're staring at ice. But what happens when we apply the second law of thermodynamics to systems bound by gravitation shocked the physicists to their core. So, unlike systems we're used to, gravitational systems have a negative heat capacity. According to the virial theorem, this means that when they lose energy, they actually get hotter, which is unexpected. It's like a bowling ball. Agony, agony. Just wait.